Hello everyone. Today we are going to analyze this frame using flexibility matrix method. In this frame there is a beam AB and a column BC. In the beam there is no load. In the column BC we have a point load 48 kilonewton. It acts in the center. Length of AB is 4 meter and the height of BC is 6 meter. Now let us find the degree of static indeterminacy. In the point A, there is a fixed support. In the fixed support, there will be horizontal reaction, vertical reaction, and movement. In the point C, there is a hinged support. In the hinged support, there will be horizontal reaction and vertical reaction. So the number of unknown reactions and moments are 5. The available equilibrium equations are 3. The degree of static indeterminacy will be 5 minus 3, so it will be 2. From the point C, let us release the horizontal reaction Hc and the vertical reaction Vc. So the point C becomes a free end. This frame is called the released structure. Let us draw the coordinates diagram. Let us keep Hc as the first coordinate and Vc as the second coordinate. Let us assume that Hc is acting towards the right side and Vc is acting upwards. Finally, if we get any negative value, that means our assumption is incorrect. We have to change the direction. We know the equation which is used in the flexibility matrix method. In this analysis, there are two coordinates. So inside the P matrix, delta matrix and delta L matrix, there will be two values. The size of the flexibility matrix will be 2 cross 2. That means inside the matrix, there will be 2 rows and 2 columns. Our first coordinate is Hc. So P1 will be Hc. Our second coordinate is Vc. So P2 will be Vc. In the point C, there is no sinking or yielding of the support. In this case, delta 1 and delta 2 will be 0. This is a 0 matrix. 0 matrix will be 0. Finally, we will get this equation. Now let us take the released structure. To find these displacements, we are going to use unit load method. We have to find the moments M, M1 and M2. First, we are going to find the moment M. Using the loads in the released structure, we have to find M. We have to make sections. Let us keep this point as D. In this frame, there are three different parts, AB, BD and DC. So we have to make three sections, one in AB, one in BD and one in DC. You can see that I have made three sections, one in AB, one in DB and one in DC. These two sections I have made at a distance of x from C, and this section I have made at a distance of x from the point B. Now let us make a table. In the table, first let us enter the members. We know that there are three members, CD, DB and BA. Let us enter them. For the sections in CD and DB, the origin is C, and for the section in AB, the origin is B. For CD, the limit is 0 to 3. For DB, the limit is 3 to 6. And for BA, the limit is 0 to 4. Now we are going to find the moment M. We need to follow left-hand side rule. Clockwise will be negative and anti-clockwise will be positive. Let us find M in CD. Up to the section there is no load, so the moment will be 0. Let us find M in DB. Up to this section, we have a horizontal load 48 kilonewton. It is acting in the clockwise direction, so that it will be negative. We have to take this distance. This distance is x minus 3. Let us find the moment m in BA. Up to the section, we have only the horizontal load 48 kilonewton. It is acting in the clockwise direction, so that it will be negative, and the distance is 3. 48 into 3, we will get 144. Now we are going to find the moment m1. We need to remove all of the loads from the frame, and we have to apply unit load in the direction of HC because it is our first coordinate. You can see that I have applied unit load in the direction of HC. Let us find M1 in CED. Up to this section, we have only the unit load. It is acting in the anti-clockwise direction, so that it will be positive, and the distance is x. 1 into x, it will be x. Let us find M1 in DP. Up to this section, we have only the unit load. It is acting in the anti-clockwise direction, so that it will be positive, and the distance is x. 1 into x, it will be x. Let us find M1 in BA. Up to this section, we have only the unit load. It is acting in the anti-clockwise direction, so that it will be positive, and the distance is 6. 1 into 6, it will be 6. Now we are going to find the moment m2. For that, in the direction of VC, we have to apply unit load. You can see that in the direction of VC, I have applied unit load. Let us find m2 in CD and in DP. Up to these two sections, we have only the unit load. But for this load, there is no perpendicular distance. In this case, the moment will be 0. Let us find M2 in BA. Up to this section, we have only the unit load. It is acting in the anti-clockwise direction, so that it will be positive, and the distance is x. 1 into x, it will be x. Using this formula, we can find delta 1L. For CD, the moment m is 0, so no need to do the integration. We can directly apply 0. For DB, the limit is 3 to 6, and for BA, the limit is 0 to 4. Then we can apply m and m1. Using a calculator, we can do these integrations. For delta 1L, we will get this. Then using this formula, we can find delta 2L. Using this formula, we can find delta 11. Using this formula, we can find delta 12 and delta 21. And finally, using this formula, we can find delta 22. We have found all of the displacements. In this equation, let us apply them. We can ignore EI because it will be eliminated. We need to find the inverse of this matrix. Using a calculator, we can find the inverse. Then by multiplying these two matrices, we will get HC and VC. For HC and VC, we have got positive values. That means our assumptions are correct. We know that in this frame, there is no vertical load. In this case, the values of VC and VA will be same, but they will be acting in the opposite directions. VC is acting upwards, so VA should be acting downwards. Then using this rule, we can find HA. To find MA, let us take moment about A from C. VC is acting in the anti-clockwise direction, so that it will be positive, and the distance is 4. HC is acting in the anti-clockwise direction, so it is also positive, and the distance is 6. This load is acting in the clockwise direction, so that it will be negative, and the distance is 3. Let us assume that MA is a hogging moment, so it will be acting in the anticlockwise direction, so it is positive. For MA, we will get minus 18. That means our assumed direction is incorrect. MA is not a hogging movement, it is a sagging movement. We have to change the direction. You can see that I have changed the direction into clockwise. Using the right hand side rule, we can find the shear force values for the beam AB. For the beam AB, there are only two perpendicular forces, this one and this one. Using them, we can find the shear force values. Now let us take the column BC. Here there are three perpendicular forces, 30, 48 and 18. Using them, we can find the shear force values. Suppose it is difficult, you can assume that BC is horizontal. In the point B, we have 30. In the point D, we have 48. And in the point C, we have 18. Now, using the right hand side rule, we can find these values. Here you can see the shear force diagram. Using the right hand side rule, we can find the moments in the point A and the point B. Let us find the moment at A. In the point A, we have MA, which is acting in the clockwise direction, so that it will be positive. Let us find the moment at B. MA is acting in the clockwise direction, so that it will be positive. BA is acting in the anticlockwise direction, so that it will be negative, and the distance is 4. Finally, we will get minus 36. We know that the point C is a simply supported end, so the moment will be 0. To find the moment at D, we can use left hand side rule. For VC, there is no perpendicular distance, so we should not consider this. HC is acting in the anticlockwise direction, so that it will be positive, and the distance is 3. For the moment at D, we will get 54. Here you can see the bending moment diagram. If you plot this diagram in the opposite sides, that is called the bending moment diagram on the tension side. Alternatively, we can draw the bending moment diagram by superposition method. First, we need to draw the free moment diagram. Then we have to draw the end moment diagram. When we combine both of them, we will get the bending moment diagram. Now we are going to end this session. Thank you for watching this video.